Question 1. Why quantum physics is named as it is? Answer. In 1905, Albert Einstein explained the photoelectric phenomena by assuming that light can be absorbed in certain packets only. He suggested that light has an elementary quanta, the photon, as it was then called. This contributed to the birth of a new physics in an important way. Many other quantities that were previously considered continuous were also discovered to be quantized. Thus the emerging new physics was named quantum physics. Question 2. So the essence of quantum physics is that everything has quanta? Answer. Not really. In fact, it is not even true. For example, if we take an H atom, we find that it has certain energy levels, but it is not true that energy is quantized. If we now take a different atom, we find different energy levels. The actual level does not reflect some universal property of energy, rather, it is specific to the system in question. By the way, such things can happen in classical physics too. For example, if we have a chord, it can only vibrate at certain frequencies. However, different chords can vibrate at all sort of different frequencies altogether. In classical physics, there is no natural unit of frequency. Question 3. Then what is the essence of quantum physics? What makes it so different from classical physics? Answer. Quantum physics takes account of the uncertainty present in nature. By the way, you should also note that quantum physics is not a single theory, rather, it is a general framework. More specifically, one talks about quantum mechanics, quantum thermodynamics, quantum field theory, etc. Here the word uncertainty is not meant in the sense that we don't know something, so that we would be uncertain of something. Quantum physics claims that reality isn't something crystal clear. Instead, it is somewhat misty. When we describe the electron's position in an H atom by a certain spherical cloud, we do so not because we are not sure where it is, which would be a simple lack of information on the observer's side. Rather, the electron itself is not sure about its position, intrinsic uncertainty, and in some sense it is really both here and there and a little bit all around. Question 4. So quantum physics must use probability theory? Answer. Yes, but it uses a built-in probability theory which is different from the classical one. There is actually a mathematical difference between probabilities arising from lack of knowledge and intrinsic uncertainty. When we use classical probability theory, we tacitly assume that at each experimental round, each measurable quantity described in the theory by a random variable assumes a value independently from the fact whether we have measured it or not. In reality, at each experimental round we can only measure some quantities. It turns out that the statistics emerging from experimental data actually contradicts the assumption that at each experimental round all quantities had a value, and that only we did not know them. On the other hand, the probability theory used in quantum physics does not make such assumptions, and in fact the predictions made by using quantum physics are in perfect agreement with experimental data. From the point of view of abstract mathematics, the main difference is that the event lattice used in classical probability theory is distributive, whereas the one used by quantum physics isn't. Question 5. What is meant by degenerate and non-degenerate state? Answer. Degenerate state. For various combinations of quantum numbers, if we get same eigenvalue, energy levels but different eigenfunctions, then it is called degenerate state. Non-degenerate state. For various combinations of quantum numbers, if we get same eigenvalues, energy levels, and same eigenfunctions, then it is called non-degenerate state. Question 6. How about the particle-wave duality? Answer. It is just another example of uncertainty. Consider light, which was already mentioned in the beginning of our discussion. It can only be emitted and absorbed in certain units. This is what has suggested the photon theory. Yet to describe its propagation, one is forced to talk about waves, even if we deal with a single photon. Actually, this is true not only for light, it is a general fact regarding every elementary particle. So from the classical point of view, the situation is rather paradoxical. A particle can sometimes behave like a wave. From the point of quantum physics, there is no paradox. The particle is a particle, but its position is uncertain. It can be both here and little bit also there. So actually even a single particle can produce interference phenomena. Question 7. Why is it that sound waves are not normally considered as having particle-like properties or raindrops as having wave-like properties? Answer. The wavelength of a wave is related to its momentum and the Planck constant by the equation L equals h/mv. For sound waves, their wavelength is too long, hence the sound particles have too little momentum to exhibit particulate properties. For raindrops, due to their large mass and hence momentum, their wavelength is too short for them to undergo significant diffraction. Diffraction can only be observable if the dimension of the aperture is comparable to the wavelength of the wave. Question 8. Explain qualitatively the phenomenon of quantum tunneling of an electron across a potential barrier. Answer. An electron is considered as a wave function. The probability of finding an electron is directly proportional to the square of the amplitude of the wave function. When the wave function of an electron encounters a potential barrier, its amplitude decreases exponentially. For a narrow barrier, the wave amplitude may not become zero after the electron passes through the barrier. Hence, there is a non-zero probability that the electron will be found beyond the barrier. This process is called quantum tunneling. Question 9. What is meant by energy spectrum of a black body? What do you infer from it? Answer. The distribution of energy for various wavelengths at various temperatures is known as energy spectrum of a black body. Inference. When temperature increases, the wavelength decreases. The total energy emitted at any particular temperature can be found with the help of the area traced by the curve. Question 10. Describe and interpret qualitatively the evidence provided by electron diffraction for the wave nature of particles. Answer. When a beam of electrons passed through a thin film of crystal, the dispersion pattern of the emergent electrons produced on a screen is observed to be similar to the diffraction pattern produced by a beam of X-ray. This phenomenon provides evidence for the wave nature of particles like electrons. Question 11. Distinguish between emission and absorption line spectra. Answer. An emission line spectrum of an element consists of colored lines on a dark background, while an absorption spectrum consists of dark lines on a colored background at the same discrete wavelength positions for the same element. For emission spectra, electrons transit from a higher energy level to a lower energy level. For absorption spectra, electrons transit from a lower energy level to a higher energy level. Question 12. Explain how spectral lines show discrete energy levels in an atom. Answer. An emission spectrum consists of a set of discrete wavelengths. A photon is emitted from an isolated atom when one of its electrons transits from a higher to a lower energy level. Energy of the photon is equal to the energy difference between the two levels involved in the transition. Question 13. What are the 4 results of the photoelectric effect experiments? Answer. Current is proportional to intensity. This result can be explained using wave nature and particulate nature of light. For every material of cathode irradiated, there is a threshold frequency below which no electrons would be emitted from the cathode regardless of light intensity. This result can be explained using the particulate nature of light only. The maximum kinetic energy of emitted photoelectrons depends only on the frequency of the incident radiation and not its intensity. This result can be explained using the particulate nature of light only. The emission of photoelectrons starts with no observable time lag, even for very low intensity of incident radiation. This result can be explained using the particular nature of light only. Question 14. What is black body and what are its characteristics? Answer. A perfect black body is the one which absorbs and also emits the radiations completely. In practice, nobody is perfectly black. We have to coat the black color over the surface to make a black body. Black body is said to be a perfect absorber, since it absorbs all the wavelengths of the incident radiation. The black body is a perfect radiator because it radiates the entire wavelength absorbed by it. This phenomenon is called black body radiation. Question 15. Mention the applications of electron microscope. Answer. It has a very wide area of applications in the field of biology, metallurgy, physics, chemistry, medicine, and engineering. It is used to determine the complicated structures of crystals. It is used in the study of celluloids. It is used to study the structure of microorganisms such as virus, bacteria, etc.